Hello and welcome to my video. I am South Korean, living in Seoul, South Korea, and that says two things about me. First, it explains why my English accent is so weird. It's because English is not my first language. And second, it means that I am very familiar with South Korea's college Scholastic ability test, which is the extensive test that the high school students of South Korea take in order to apply for the college. And I have already uploaded one problem from the very same test as this one. So if you haven't seen it yet, please check the link at the top right corner. And today we are going to take a look at this problem. So it says the figure shows the graph of continuous function y equals fx. So there's the graph. And gx, which is the inverse of fx, exists and is continuous on the closed interval 0, 1. Then this limit n goes to infinity, sigma k from 1 to n, g k over n minus gk minus 1 over n times k over n. So this limit is equal to, then we have a multiple choice. The interval of integration is all from 0 to 1, and choice 1 is integral gx dx, and choice number 2 is integral of x gx dx, and choice number 3 is integral of fx dx, choice number 4 is integral of x fx dx, and choice number 5 is integral of fx minus gx dx. Like many challenging or important problems, I encourage you to try to solve this problem all by yourself. So if you're actually going to do that, pause the video right here for a moment, and for the rest, I will present you the solution. First, since the problem contains gx, which is the inverse of fx, we need to understand how we can denote the values of the function gx. One way to do that is using the fact that the function and its inverse is symmetric with respect to y equals x. Then we can sketch the graph of y equals gx by flipping the graph of y equals fx over y equals x and use that graph to denote the values of gx. So if fa equals b, then using symmetry, we can sketch in the figure like this, gb equals a. There is also another way. You see, instead of flipping the graph with respect to y equals x, we can think of this y-axis as the new x-axis for the inverse gx, and this x-axis as the new y-axis for the inverse gx. This has the same effect as flipping the graph of y equals fx with respect to y equals x. Then we can indicate the values of gx using the graph of y equals fx like this. So if this coordinate is x1, then this is gx1, and if this is x2, then this is gx2. And this is the approach that I am going to use when solving this problem. Alright, now let's get to the actual problem. First, let us take a look at these x values. We are dealing with gx right now, so we are thinking on the y-axis of the plot of y equals fx. So this is the x-axis for the inverse function g. Now, if we partition the interval 0, 1 on the y-axis into n uniform subintervals, then the coordinates of the n plus 1 points that partition the interval are, so we start from 0, then we have 1 over n, then 2 over n, then at some point we have k minus 1 over n and k over n, all the way up to 1. Therefore, gk over n and gk minus 1 over n can be marked on the original x-axis using the graph of y equals fx, like this. Therefore, this distance right here is gk over n minus gk minus 1 over n, which is this part. Moreover, this length right here is k over n, which is this part. Therefore, this gk over n minus gk minus 1 over n times k over n is equal to the area of this rectangle. Next, we carry out the summation from k equals 1 to k equals n. So this sum means that we add up the areas of these rectangles. Now we take the limit n goes to infinity. This means that we divide this interval 0, 1 into infinitesimally small subintervals. So the width of each rectangle becomes infinitesimally small, and we have infinitely many small rectangles. Therefore, the sum of areas of these rectangles must approach the area between the graph y equals fx and x-axis on x from 0 to 1. We know that this area can be expressed as the definite integral from 0 to 1 fx dx. Therefore, if we take a look at the choices, we can see that the correct choice is 3. And that is our answer. So we have found the answer, but here I want to spend a little more time and talk about why I like this problem and selected this particular problem among vast problems of Korean College Scholastic Ability Test. I said that this is the test for high school students. High school seniors who take this test must have practiced many problems on calculating the sum of the series using integrals. And perhaps the most famous trick is this. Change k over n in the series into x, change 1 over n into dx, and let the interval of the integral be x from 0 to 1. Then we can convert this type of series into this definite integral. For example, for the series like this, we can change it into this integral. So this k over n becomes x, and this 1 over n becomes dx. Then we can carry out the integration and obtain the answer. The thing is, many students simply memorize this trick and use it to solve problems without the proper understanding as to why this trick works in the first place. If you draw the rectangles like we just did previously, you can easily understand why this trick works. So we divide the interval 0, 1 into n subintervals with uniform lengths. Then the x-coordinates are 1 over n, 2 over n, and we have k minus 1 over n and k over n here, all the way to 1. And this height is fk over n, and this width is 1 over n. So this individual term is the area of this rectangle, and by this sigma, we add up the areas of these rectangles. And by the limit, the rectangles become infinitesimally small and infinitely many. So we have the area under the graph y equals fx, where x is from 0 to 1, which is how the definite integral is defined in the first place. But in the previous problem, this trick doesn't work. Whoever come up with this problem twisted the common series to integral problem a little bit using the inverse function, so that the rectangles are constructed slightly differently from what we just saw. So here you cannot find the answer by simply trying to do stuffs like changing k over n into x or etc. You must be able to interpret the meaning of this summation by constructing the rectangles by yourself. And you have to have a solid understanding of how the limit of this area of rectangles becomes the integral. So this problem does not check whether students have memorized the trick of converting series into integrals. This problem checks whether the students understand the underlying mathematical principle of how the sum of areas of rectangles and the definite integral is connected. And that is the reason why I like this problem. Thank you for watching, and please click that like button and subscribe for more math videos, and I will see you in another video.